Thank you so much. It's a pleasure to be here, and thanks to the organizers and to IPAM. I will talk about my recent work with Ajit Guna, which was posted on Archive in December last year. So I will start with the general introduction on lattice paths that you've seen before. And then I will define a partition function that I would like to compute. And the calculation is heavily based on an algebraic tool, which is shuffle algebras, which is part of the title. I will show you some parts of the calculation. And then after that, if I have time, hopefully, I will tell you how this partition function can be applied to calculating skew Macdonald polynomials. So lattice paths, we consider a square lattice, as in previous talks. We have a rectangular domain, and we look at lattice paths in this domain. These are conventions, same as in Filippo-Stock, not the same as in Phillips-Stock. And so the rules are that the paths are starting at the bottom or on the left edges, and then they have to end at the top or right edges. What's that? Sorry. So now we can fix external edges to be occupied by paths or unoccupied, and we will be using zeros and ones to denote occupation and unoccupation. So for these particular boundary conditions, we will have this kind of configurations. You can see that 1 corresponds to a red path and 0 corresponds to the absence of a path. And now we can generalize this picture to a colored version. Now we have the same square grid, and on this grid we will put colored paths. In this example, I have two colors, red and green, but the number of colors is unrestricted. You can imagine any number of colors. And again, they follow the same rules as in previous talks. They start at the bottom and left and end at the top and right edges. And the boundary conditions are fixed by integers 0, 1, and 2 in this particular case, but with more colors, we will have to use more numbers. And these are particular examples with this kind of boundary conditions. Now, boundary conditions. There are special kinds of boundary conditions that were considered before in previous talks. Domain wall boundary conditions, very famous example. And here are a few examples of lattice paths with domain wall boundary conditions. There are 3 examples missing here. But this is what we get in the 3x3 case. Among examples from the colored version, we have the so-called rainbow boundary conditions. So we have zeros and then a sequence of different colors. And in this particular case, we have these examples. So if you look carefully at these 2 cases, you might notice that in the colored case, you will have many more configurations than in an uncolored case. So if you want to color these paths, make them all different colors, you will find bijection between these particular configurations. But if you try to color this configuration, so blue, green, and red, you will find that there are 2 possibilities. So blue can go like this, but it can also exchange with the green. So this is just saying that the rainbow configuration is a little bit more rich than a single color configuration. So these are our lattice paths. And now I would like to generalize slightly these boundary conditions. I would like to consider a generating function of domain wall type boundary conditions. So here we have I, j, k. They denote different paths of different colors, and they can run over any integer set. So you can have any number of colors. But the important part here is that I matches with this I matches with this I, and this j matches with this, and k matches with this k. So this is like a trace. So whatever path is here, it has to end up over here, I, unless it coincides with J. And to have some control over such boundary conditions, I will put parameters zi, zj, zk, so that if I would like to pick up a particular boundary condition, I can just ask for the coefficient, for the monomial corresponding to the content of the colored paths. So because this is a sum, we can just join the lines together like this. So we have a picture of this. So if you draw this on a piece of paper, joining lines implies connecting edges of the paper like this. So you have a square piece of paper, you draw a lattice, and then joining lines implies connecting two neighboring edges of paper. So, and that results in a cone, which has a singularity which will play a role later. So we have lattice paths on a cone, and in the colored case, this is a particular example when we have a single. So we consider such a partition function, such a set of configurations, and we pick up one red Z1, which corresponds to a single red path, and Z2, which corresponds to a single green path. We will have many configurations, and these are some examples of those configurations. And they can be also drawn on a cone. It's just so about the cone. I rotated this picture. I folded the paper like this, and then rotated the picture like this. So you can see that this path here is this one here, and so on. So these are kind of boundary conditions that I would be interested in this talk. And next, I need to introduce the Boltzmann weights. So we have many different colored paths. And I would use a red and green to denote different colors. And we have, if we look at a particular local configuration, we will see different vertex configurations. And these are representative examples of what you can see locally. If you look at only one color set, like red, you will figure out that you have 6 configurations. This corresponds to the 6-vertex model. And if you have many different colored paths, you'll have this kind of pictures, where you'll have to substitute red and green with other colors. But this is what you will get. So you can imagine here that red is a color I and green is color J. And for these local configurations, we would like to introduce Boltzmann weights. And these are the Boltzmann weights that we choose. We introduce the parameter T and the parameter U, where U is called the spectral parameter. So these Boltzmann weights are coming from the R matrix of U T SLN quantum group, which I will come back to later. So now the question is, let's take n by n lattice, look at all possible configurations, and compute partition functions with arbitrary boundary conditions. So they're denoted by Z, and then we have arbitrary boundary conditions here denoted. So the boundary conditions they range over different integers from 0 to n, where n is the number of paths, and we would like to compute this kind of partition functions.
On the first line of vertices, you just choose the one, or which kind of weight do you have for the first line?
This one.
And for the second line?
For the second line is the same weights.
Okay, so there are
yeah.
2 vertices with the same weight.
Yeah.
Okay.
Yeah, so this weight corresponds to both of these vertices.
Color or nothing is the same.
Yes. Yeah. So you may think of the empty line as being high color.
Okay.
Like the infinite.
Yeah, but then the last one should be green on.
These are the same colors.
And so they are both one.
Yes. You can have a green one, and it will have a one as well.
Thank you.
So now we're interested in this kind of partition functions. So this is equal to a sum over all configurations, weighted configurations, with these particular boundary conditions. So these are products of all these Boltzmann weights corresponding to a particular configuration that I gave examples of previously. And moreover, we would like to generalize this, of course, with, to use different spectral parameters for different lines. For example, in this case, 2 by 2 case, we will associate spectral parameters with horizontal and vertical lines. So the x spectral parameters correspond to the horizontal lines, and the y spectral parameters correspond to the vertical lines. And in this particular case, we have 2 configurations. We can use the Boltzmann weights from the previous slide and calculate individual contributions from these configurations. I'm sorry. And this configuration will contribute this rational function, and this one will contribute this rational function. So that's how we compute partition functions in this setup. It's quite convenient to use R matrices because they encode all configurations. We can use these R matrices to calculate generic partition functions. So the R matrix schematically is represented by a cross with arrows. It's a matrix, so it's good to have arrows because they will tell us how to multiply these matrices, in what order we're gonna multiply these matrices. And in the particular case of a single color, we get a 6-vertex R matrix. And I would like to stress here that we're using a parameter T, not a parameter Q that is commonly used. So this R matrix is from UT SL2 hat. But more generally, we will have n colors. So the parameter is T. So you can look at if you pick a particular configuration over here, 0, 1, 2, and so on, you can read off the Boltzmann weights from the previous slide, and you can come up with this matrix. And yeah, this shows how the Boltzmann weights are matching the configurations. Now we can put together these R matrices and verify the famous Yang-Baxter equation, which is of course at the core of all this business. So now, as I said before, R matrices are very convenient to calculate these partition functions. And so we stuck together a bunch of R matrices, and we basically use this cross to form this square lattice. So if you want to calculate a particular partition function, you can take that matrix over there and just ask for a particular matrix element of that matrix. So which is this computed using a product of R matrices, and we just ask for a particular coefficient. So now I would like to introduce the second parameter, which is called Q. And the way I do it, I equalize. I make the vertical spectral parameters proportional to the horizontal spectral parameters. This is really this is an idea by Paul Zindustan to do this. He made this wonderful observation a couple of years ago, which gave rise to all this business. So the next step is to formulate the partition function that I would like to compute in the following. So I'm taking this kind of configurations, and I'm gonna equalize gammas and deltas, and then otherwise consider this to be domain wall. So alpha and beta are 0. Sorry. So this is the partition function that I would like to compute. And the parameters z's are keeping track of the types of particles that I have here, of paths that I have here. So this is a conic partition function because we can put it on the cone, as I showed you before. And it's quite convenient to calculate the generating function of this object. So we consider all lattice paths of all sizes, and we associate a parameter v to a particular size, And then we ask, what is this partition function? So this is a famous object. This is like a grand canonical partition function, statistical mechanics. And in non-interacting systems, these kind of partition functions are known to be exponentials of some integral. But we are dealing with the interacting particle system. But our interacting particle systems are Yang-Baxter integrable. So the hope is to find an exponential formula for a partition function with the catch that the exponents are operators. And this is what we do. So I'm going to give you the answer. This is the main result of our paper from December last year with Ajit. We calculate the partition function of the generating function of the partition function, this trace partition function, this object. So we calculate this object, generalized boundary conditions, and we find an exponential formula. So as I said, this can't be a pure exponential, like exponential of scalars. These exponents have to be operators. And in the rest of my talks, I will explain what kind of operators they can be. So I can tell you now that these exponents, they are themselves partition functions of the same type. And you can multiply, this tells you that you can multiply. There is a certain kind of multiplication that takes two partition functions and produces another partition function. So you have an algebra on partition functions of the type that I was talking about before. And in this formula, you can notice that this is an n-colored model, and every color comes with its own spectral parameter, with its own parameter. And they are all, they contribute the same kind of factor. So
as operators, what do they act on?
This is abstract algebra, which has representation theory. And I will use representation theory in the application part. There are several representations of these objects. So if you're thinking about quantum affine Lie algebras, if you're thinking about basic generators of quantum affine Lie algebras, they will be contained in this part. So of course, important part here is that this object L is part of an algebra, and it will have to be part of a commutative algebra, because otherwise the exponential will not make sense. So now I'm turning to a more technical part of this talk, which is about the algebraic reason behind this formula. So this algebraic structure is called the shuffle algebra. We start with the vector space of symmetric rational functions in k variables, which have coefficients rational functions in Q and T. And we define a multiplication of this sort. So we take two symmetric rational functions, f of x1 to xk, and then we multiply another symmetric rational function, x1, xl. And I would like to rewrite slightly this formula. Maybe it's more convenient to see it like this. So we take subsets of indices 1 to k plus l. We take the first function to depend on the first set of indices. And then we multiply this function by the second one, which depends on the second set of indices. This is complement set. And then we multiply this by the cross term, which is over there. It depends on the first set and the second set of indices. Complement. So this is called the shuffle product, and this will be very important. So this forms this is a product which will be a product of partition functions. And the important part in this algebra is that we can represent these rational functions as a Laurent polynomial divided by a certain factorized polynomial, which tells us what kind of poles this rational function has. And the Laurent polynomial here has to satisfy a certain kind of set of conditions in which you can take a triple of any arguments, and if you set them to have certain ratios, as shown here, then they have to vanish. So the important message here is that when you take two functions which satisfy these properties, if you insert them in that product here, this cross term is designed in a very special way so that this whole object will still satisfy these will conditions. It takes a little bit of time to understand why this is true, but you can, if you impose will conditions, you can design this shuffle product in such that the product of two such functions will still satisfy the will conditions. This is important because this makes it into an algebra. So now we have a so-called shuffle algebra. And in order to appreciate that this is actually a non-trivial product, you can take x1 to the power k, x1 to the power l, calculate it. So this will be given by two terms. So this will have the term a plus b. Then you can calculate x1 to the power l and x1 to the power l. So the reverse. Yeah, thank you. And then compare the answer. And in general, this will not be the same. So this is not a commutative product. It's actually a very, very complicated product. It's not a commutative one. But inside this algebra, there is a commutative subalgebra, which will be the main focus. So there are functions in x1, x2, x3, and so on, which commute under this multiplication. And there is a condition which I cannot explain why this is an essential condition for this multiplication to be commutative. But so there is a condition. You take a subset of arguments, and you send them to 0 or to infinity, and they have to give you a finite limit. And those limits have to coincide. This was a result of a few big papers. So in the rest of the talk about this shuffle algebra, I will focus on the commutative subalgebra. So everything I will talk about later will be about rational functions which commute with respect to this product. So I will give you a few examples, which will play a role later, of this commutative subalgebra. So the first thing when you encounter a shuffle algebra, you should think about something that the simplest kind of element of the shuffle algebra. So what is the simplest rational function that satisfies will conditions? And this is what Feign and Odesskii figured out. They looked at the factorized elements. So if you look at this rational function, and for p, if you insert any of these values, you can directly check that they will satisfy will conditions. And these rational functions will be also commuting. So if you take E1 star E2 and compare it with E2 star E1, you will find out that they are equal. This is a very non-trivial computation, and this took a very long paper for Feign and company to prove this. Another element of this commutative shuffle algebra is given by a determinant which is precisely of Easter-Karepin type, which appeared before in a few previous talks. So you take this determinant, and for p prime you can use q, for example, and for p double prime you can use t inverse. This gives a determinant, and you'll need to fix this function to cancel some poles, as you usually do with Ising-Kreppel determinants. And after you do that, you can check wheel conditions, and this will be another candidate for the commutative shuffle algebra. Another shuffle algebra element is slightly less familiar. It's given by a symmetrization of some rational function. So this rational function appeared in the work of Andrei Negutz in a relation of quantum toroidal algebras. So the reason why I mentioned this element here is because there is a connection between E, H, and S. And here is the connection. So these are formulas which I can't afford to spend time on to prove them, but this formula was proved in Andrei Negutz's work, and this was proved by Ajit and myself. So the generating functions of these elements are given by the exponentials of these elements. And the generating function of determinants are given by similar exponentials. So if you look carefully at these two formulas, they're opposite, they're inverses of each other. So I'm using letter E and H here, not randomly. I'm trying to make connections with the symmetric functions. So E are elementary symmetric functions, and H's are homogeneous complete symmetric functions. And they have similar exponential formulas in terms of power sum symmetric functions. So the hint here is that this Sk is the power sum symmetric function. It plays the same role as the power sum symmetric function for the elementary symmetric functions and for the homogeneous symmetric functions. This is completely analogous to the theory of symmetric functions. So this is a little lemma that I will use later. So now let's get back to the partition functions. This kind of partition functions. So I had the x parameters here, x1, x2, x3, and here qx1, qx2, qx3. Now I'd like to claim that this kind of partition functions, they are actually elements of the shuffle algebra. So they are symmetric functions. And, So they are elements of the commutative shuffle algebra. The proof consists of checking the definitions of the shuffle algebra. First of all, we prove that they are symmetric in the x parameters, and this follows standard Yang-Baxter logic. We put a crossover here, our matrix, and then we use the Yang-Baxter equation to push it to the other side, and then we use the trace property to push it here. And then again, we use the Yang-Baxter equation, and then we can remove this cross. So at the end of the day, we get a symmetric function. So partition function of this type is equal to this partition function where the parameters x are swapped. And then we can look at these partition functions more carefully and prove the wheel conditions. And the type of computations that you need to do to prove these wheel conditions are of similar spirit as you do Karepin's characterization of the main wall. So you look at freezing, you look at what happens with the paths. So you can prove these wheel conditions in exactly the same kind of computation. And you can also prove that these elements are parts of a commutative shuffle algebra by using the same kind of computations. And so you can take some parts, some variables to go to 0 or to infinity, and you can show that they give the same limits. So now this Tn, that partition function, is an element of the shuffle algebra. And let's calculate it. So this element is a trace of a certain matrix. So here is the matrix. So it depends on parameters y and x, and y's are taken to be qx, and we have domain wall boundary conditions, generalized type. So we would like to calculate the trace of this matrix. And the way we do it, we will use the so-called F basis. It's a special technique from quantum integral models, which says that there exists a matrix F such that if you take this combination of your matrix W, so this is a conjugation by F, then the transformed matrix W tilde will satisfy a special type of relations. So what are these relations? These relations tell us that let me generalize. So these relations tell us that if you multiply by a permutation matrix on the right by this matrix, you will get the same matrix with permuted arguments. And on the left, you will have the same matrix permuted with the y arguments permuted. So I can multiply this recursively, and I can have any kind of permutation here. So in general, this formula looks like this. So P sigma is a collection of permutation matrices. And this is equal to the same matrix where x's are permuted. And if I multiply by P sigma on the left, this will give me the same matrix where the y's are permuted. So what does it tell us? It tells us if you want to calculate a matrix element of W tilde, you can choose any other matrix element that you can calculate, and then just permute the arguments. So it's enough to calculate a single matrix element of W tilde to get all of them, just by permuting the arguments. So the trick here is that let's find the simplest matrix element of W tilde that we can calculate. We calculate it, and then we'll get all of them.
Quick question.
Yeah.
You say there exists a transformation. Is it like explicit, like nice?
It's very explicit.
Okay.
It's an explicit matrix,
That's
which is.
not so abstract.
Yeah, I don't want to write it down here.
Okay.
Yeah, yeah. It's given in our paper and in other papers as well. Yeah. So we calculate a particular matrix element which has k ones and n minus k zeros, and the other matrix, the other index is the reverse of the first one. So this matrix element is given by some factor, which comes from this F, and then it's given by the original matrix element of this partition function. And this thing we can calculate.
Sorry. I would expect some factor or y-depending factor as well, or not?
Okay, this is. Well, there is no y factor for reasons related to a particular choice of f. So these factors are coming from here. This will produce a factor equal to 1, just because of the structure of f. So now the question, can we calculate this? And let me draw this in this form. So this partition function is equal to this. And if you look at this carefully, you will see that most of this partition function is frozen, and there is a single domain wall boundary condition over here, which is equal to the Zergin determinant. And the Zergin determinant is has an explicit form, so we will. This is a determinant. So now we calculated a particular element of W tilde, which is equal to a product, another product over here, and a determinant. And by this statement over here, we get all matrix elements of W's, of this matrix W. So W tilde. And because this is a trace, this W can be substituted with W tilde, so we calculate Tn. So on this slide, I show you how to calculate Tn. So we have an explicit formula of Tn. And the rest is to do some algebraic manipulations to show that this Tn can be rewritten as a shuffle product. So there is a summation in Tn, which can be rewritten as a shuffle product of two elements that I showed you on the slide of the commutative shuffle algebra. This is completely factorized. This is a determinant. And I need to remind you that this was generated by an exponential genetic function. This was also generated by exponential genetic function. So if I take a generating function of Tn, I will also get an exponential generating function. So this is the answer of the conic partition function, the generating function of the conic partition function in the case of the 6-vertex model. So if you want to calculate, for example, if you would like to calculate this object with 2 red paths, so 1, 1, 0, permutation of these things, then you will have to pick up a coefficient z1 to the power 2 and z0 to the power 1 from this formula. And the shuffle, the star here was defined previously. So this can be generalized in the calculation is very similar to what I showed you before, to a generic case with arbitrarily many number of particles. And moreover, we can use UQSL n plus 1m, so a superalgebra. So we have n bosonic particles and m fermionic particles. And we associate fermionic paths with the W arguments and bosonic paths with the Z arguments, and we will get this formula. And the way you calculate this is very similar to what I showed you before. So we have this kind of generating function for this conic partition functions. And yeah. And we can actually use this generating function. So if you look here, let's remove all the W arguments except from 1. All the Z arguments except from 1. And Z0 to put to 0. Then we take a limit of W1 to Z1. This limit is a bit singular. You have to be a bit careful. But the consequence is that this LK that you can see over here is given by a partition function of precisely the same type as before. So you have I. So let's say you have 2, 2, 1. And some technical details tell you that you will have to put here the multiplicity of the 2's. So I have to equal. And you have to multiply this trace by the multiplicity of the 2's and some power minus 1 to the power k. So this gives an explicit interpretation of the exponent Lk over here, which is also a domain wall type partition function. So this object is for arbitrarily many colors, fermionic and bosonic, and this object is for a single bosonic and single fermionic color. And it has an explicit formula in terms of partition functions or in terms of symmetrization formula. So now I have 5 more minutes. Let's look at an application of this partition function. Let's remove all the bosonic particles. Let's look only at the fermionic particles. We have this kind of exponential. And this is a power sum, Kth power sum in the W arguments. It's a famous metric function. And when we see, this is known as a Cauchy kernel, a mixed Cauchy kernel. A Cauchy kernel has power sums in different set of variables. In this case, you have power sums here and something else over here. Nevertheless, this was an object that appeared in literature before. And the first thing that you might want to do with this object is expand in Macdonald functions. So you expand in Macdonald functions in the W's, and you get the Macdonald function here. And you will have some kind of element of the shuffle algebra that comes from here. So this element is known in the shuffle algebra world. And it has a few famous properties. So this element was studied, and it has the nice thing about this element is that it has certain representations which are quite special. So you can take these x variables, and if you set them to powers of q and t, they will reproduce for you Littlewood Richardson coefficients for Macdonald functions. This is parts that I have to skip. I just give you the answers from some very long works. So what is this evaluation map here? You choose arbitrary skew Young diagram, mu over nu. And these boxes, they have content. So for example, this box has content which is given by a power of q and t. So this is q to the power, the number of boxes to the left. So in this case, 3. This is q to the power 4. This box has the number of boxes to the left, 3, and the number of boxes t to the power minus number of boxes from the top, so minus 1. So any box you can, for any box, you calculate this kind of content. So this will be t to the power 2, t to the power minus 3. So this is evaluation map. So you take a shuffle element, insert number of arguments x. x1 you substitute with the content of the first box. x2 you substitute with the content of the second box, and so on. And a famous result from this work tells us we can use that result to derive that evaluation of these so-called Macdonald shuffle elements is equal to Littlewood Richardson coefficients. Now let's apply this evaluation to this exponential or to this expansion. So I'm going to apply this evaluation over here. So I will have Littlewood Richardson coefficients over here. And that will give me a formula for the skew Macdonald functions. So if you sum together Macdonald functions with these coefficients, you will get so-called skew Macdonald functions. So that exponential, shuffle exponential, reproduces skew Macdonald functions under such evaluations. And let's now recall the lattice path construction for these objects. And so this is a particular example when we look at evaluation of this type. And it will give us, so we take trace partition functions with 2 arguments here. So not 3, but 2. And we set x1 equals to q, and x2 equals to t inverse. And we calculate this partition function, the partition function with this particular choice of spectral parameters. And by the theorem before, we get this lattice path interpretation of skew Macdonald functions. So this is a monomial expansion in this W variables. And this is the end of my talk.